And to Jasper, can you see my slides?
It just minimized now, I think, once you started recording.
Oh, weird. Okay, let me try that again. Oh, weird. I see. Okay, I think it went out of mirroring mode. 1 second. Ah, okay. Nope. The cable just got unplugged. Okay. Now everyone's seeing this, right?
Nope, I can't see it still.
Oh. Can you see it? Can you see my screen now?
Sorry, no.
Oh man, okay. It must have turned, maybe it turned sharing off.
Yeah, I can see it now.
Okay, that multiple problems, sorry. Okay. Now I think we all got it. Okay. So welcome. I'm just gonna, like I said, I don't have a particular agenda. Also, I don't have a microphone, so everyone in the back, if you wouldn't, I can only talk so loud. Basically, yeah, I don't have an agenda or anything. I was going to start by showing some fun slides and then walk through a little bit of what you can find in a FreeSurfer directory and what all those weird files mean. And then I'm going to talk a bit about the library I maintain, which is largely a library for interacting with FreeSurfer in a nice way in Python. This animation is just a fun animation. I mean, I made this because I study vision. I study the visual cortex, which is the part of the brain here that's all colored. And it's colored according to the part of the visual field that that particular spot responds to. So here, there's always this, notice there's always this red kind of splotch along this particular gyrus in every subject. That corresponds to the lower visual field. That's basically this part of the brain processes this part of the visual field. And I use this animation to demonstrate to people that there's a lot of variability in the visual cortex. That sulcus in the back there, that all that color is arranged around, is drastically different in different people. And in fact, that part of visual cortex can vary by a factor of about 4 between people, whereas the brain only varies by a factor of about 1.5. So I use this animation to kind of demonstrate how big this variability is. But the reason I'm showing it today is because making this is not really possible without FreeSurfer, or without FreeSurfer and the tools that have come since. So every time one of these brains morphs into a different brain, I've got to figure out, when I'm making this animation, I got to figure out for every point on that first brain's cortical surface, where it's going to end up in the second cortical surface. And in order to do that, I have to have some correspondence of the points between the two brains. And if I just give you a brain, you don't have any idea what that correspondence is like. I mean, you can maybe guess, but you need some automated way to make those. Does that problem generally make sense to people? Why that's a problem? I am. Yeah, I am using FS average here. Yeah, so basically, in order to make these, I took the FS average brain, which FreeSurfer aligns across subjects, and I warp it into the shape of every brain, one after another. And I'm gonna, you're just a step ahead of me here. Yeah. So I guess I intended this as motivation. If you learn all about FreeSurfer, you can do this too. But real quick before I jump into actually showing you some code or looking at directories, I do have so first of all, ignore the slide for the moment. People use FreeSurfer for all kinds of reasons, not just cortical surface comparison. For one thing, FreeSurfer will automatically segment your data into gray and white matter, and that's hugely valuable. I mean, I've never had to manually segment a brain, thank goodness, because FreeSurfer's always been around for as long as I've been around. But my my advisors had to go in and manually click every voxel that was white matter and manually click every voxel that was gray matter. And so that was just like a months of work by itself. FreeSurfer does that automatically nowadays. And while you really should check your FreeSurfer segmentations yourself, for the most part, they come out really good. You rarely have to really correct them. And you almost never have to correct them so much that you need to like rerun everything. So FreeSurfer's come a long way in the last 20 years. It was written all the way back in the 90s, which I think is crazy. And it's a very powerful and useful tool. I think one of the most innovative things it does, and in fact it did all the way back in the 90s, was tell us how to compare subjects using anatomy, or how to align subjects using anatomy in a way that wasn't just about a rigid body transformation. So I've just got a few slides here that kind of explain very simply what FreeSurfer does to do this process, because I think that often this process is very opaque to people. So the reason I started using FreeSurfer was for exactly this reason. I wanted to compare maps across subjects. I wanted to compare these retinotopic maps that you're seeing across subjects, but everyone's brain is a different shape. So how do you even do that? You can do it volumetrically, but we know that that's not very good. A voxel in one subject's brain, even if they're aligned, may not even be in the brain of another subject. So that's a kind of mediocre way to do it. So what FreeSurfer realized is you can start by taking these anatomical images, these T1 weighted images, and you can just do a rigid body image alignment so that they all roughly line up to translation and rotation and that kind of thing. After that, you can just take the average of all of these images just across voxels, and you get this very smooth kind of average T1 weighted brain. And you can see, you can just look at this. I guess you can't see my pointer, but if you look at that brain in the lower right, it's clear that it's very smooth. It's not like a real brain. It doesn't have nearly enough folds in it. Whereas the other brains all have a lot more wrinkles and stuff. So this is clearly not a real brain, but it has about the right shape. And you can make a 3D model of this brain, which FreeSurfer does this part too. FreeSurfer will take your segmentation and turn it into one of these 3D models. And the idea is, okay, now we have this atlas brain. It's made from the average of a bunch of subjects, and that's the FS average brain. That's actually where the FS average in FreeSurfer comes from, is that average. And on the right, we have this individual actual human brain. So in order to do this anatomical alignment, or this anatomical normalization that FreeSurfer does, it starts by inflating these brains into spheres, because that's just easier to work with. Spheres are much easier to work with. And you can see right away that there's some correspondences in these curvature maps, that there's, I wish you could, there we go. You can see that point, right? Yeah. So it's pretty clear that like, here's the medial wall on the average, and here's the medial wall on the individual. And there's a lot of similarity here. But if we just highlight the Cochrane sulcus, which is that sulcus right there, and we move that RY to the exact same position on the other brain, they don't really line up right, and that's a problem. But what FreeSurfer realized is you could take the individual brain, this sphere, and you could treat it like a great big rubber sheet that you can stretch and compress. You can't tear it and you can't fold it, but you can stretch it and compress it. And they just perform this very high dimensional optimization where they minimize the difference between the curvature of the brain on the right and the curvature of the brain on the left by stretching and compressing the brain on the right. And that looks like this. So it's not just rotation, it's a diffeomorphic kind of warping. It's stretching and compressing things. And that's essentially the operation FreeSurfer performs that takes like 8 hours when you run FreeSurfer. It's got to do this really high dimensional optimization to align those things. But once we've done that, we've got this nice correspondence of points between the average brain and the individual subject's brain. And so if we take another subject's brain and we align them to the average, we can have a correspondence between the subjects. Yeah. Okay. So for Zoom, the question was, at the beginning, did they make the surface area equal or something? So they make the surface area equal by inflating them to spheres, because the two brain surface areas are absolutely not equal. One brain's surface area will vary by quite a bit, by a factor of like 1.5 to someone else's. But if you make it a sphere, you always make the sphere have the same radius, and that takes care of the surface area problem. Yeah. And just to be clear, the number of vertices and triangles that make up the model on the left, and the number of vertices and triangles that make up the model on the right are not the same. They're very different sets of vertices and triangles. Yeah, but that's a great question. Other questions about this process? Okay, so that's that's a very quick version of what FreeSurfer does to do quote unquote surface-based anatomical normalization. And this kind of normalization is much better if you study the cortical surface, if you study the gray matter. This kind of normalization is much better at lining up ROIs between subjects than any kind of volumetric registration. Because volumetric registration, well, I want to back off that a little bit because there's new methods where you do diffeomorphic volumetric registrations. I think FreeSurfer even supports this now. But if you're just doing a rigid body registration, these cortical surface methods are far better. They do a much better job at aligning things. They even do a better job than volumetric diffeomorphic registrations. And what I mean by that is, so we did a diffeomorphic registration because we treated the sphere like a rubber sheet. And stretched and compressed it, but not in a in a local way. You can do the same thing with the volume. You can treat the volume like a big rubber cube, and you can stretch and compress it in various places to make two brains match each other volumetrically. But when people have done that, they don't tend to get better results than when you do this with the cortical surface. So this tends to be kind of still the gold standard way to align things. Yeah. So the question is, what is the ground truth to compare it to? And I think that's a hard question to answer because, so if we're talking about something like inter-subject alignment, we typically don't have like a ground truth. We don't know that my brain and your brain are structurally the same. In fact, they're not, and they're not even functionally the same. Even if we perfectly controlled for structure, they're still not going to be functionally identical. So there is no ground truth in terms of this alignment. Instead, what we can ask is, once we've aligned everything structurally, how well do the functional ROIs line up? So in that sense, the kind of what we would replace the gold standard with is something like the ROIs line up perfectly. And that would be kind of the quote unquote perfect result for an anatomical alignment. Of course, that's never going to happen, but that said, if you do a volumetric alignment, what you get is a big blur over Cortex. And if you do a surface-based alignment, you'll get a much smaller blur in terms of the overlapping ROIs. Did that make sense? Yeah. Other questions? Okay. So those are just some kind of fun animations to show how this all works. But at this point, I'll start with the terminal here and see if I can make this big enough we can all see it. And for anyone on Zoom, please just interrupt me if you have a question. Also, people here, you can interrupt me too. Okay, so if we start if we just open up a terminal in the hub, I'm going to start by navigating to a FreeSurfer directory, and we'll just take a look at one of those. So I happen to know that there's some FreeSurfer directories in the natural scene database. So I'm going to cd to nsd, no, cd to shared, and then to nsd. Sorry? It should be. I did tell it to record, didn't I? Yeah, okay. Yeah. So I'm then going to cd to the ns data other. And then in here is a directory called FreeSurfer Originals. And then there's a whole bunch of different directories in here. These are different, several of these, like these repo1 are different FreeSurfer directories that were generated from different T1s, whereas these originals were generated from the average of all the T1s that were collected for one subject. So basically, for this first subject, there were 6 T1s collected, and you can run FreeSurfer's recon_all program on just a T1, and it will produce a FreeSurfer directory based on that T1. Or you can average all your T1s together and you can run on that average T1, and that's what's in this sub-01 original directory. Does that make sense? Or should I talk about recon_all? My sense is almost everyone has used recon_all at some point, but if you want me to talk about recon_all, I'm happy to talk at least a little bit about it. Yeah, okay. So I think that's probably a very universally held belief or feeling that you've run recon_all, but that you don't really know what it does. And I feel kind of similarly. I actually think that the best resource for this is if you search for recon_all dev table, there's a recon_all dev table on the FreeSurfer wiki, And this actually has step-by-step everything that Recon runs and what the inputs are and what the outputs are for that step. And there's a lot of information here. This is very dense, and a lot of what it's doing is feels like details. It's important in the process, but it's not something we think about very much. So like, for example, there's various kinds of ways of making sure the axes are right, and then making sure that the contrast is kind of uniform and normalizing the contrast across the image. And there's of course skull stripping and identifying the brain, and lots and lots of steps that it performs. The way I would characterize it is there's 2 or 3 stages of Recon. The first one really is just volumetric stuff, where they take the T1 that you've given it, and they it goes through and it figures out where the brain is and strips the skull and makes sure everything is labeled and that kind of stuff. And then the second stage is all about making the surface model. So this involves figuring out where the cortical white matter surface is, where the cortical or the peel surface is, and coming up with tessellations of those. So they do you all know what I mean when I say tessellations of the surface? This is okay. Let me actually show you something in a notebook real quick. So I'm gonna just real quick launch a kernel. You're welcome to follow along with me on this, but I'll come back to this later. I'm going to import NeuroPython as ny. This is NeuroPython is the library I maintain, which is a big part of it is dealing with FreeSurfer subjects. I'm going to say sub equals ny.freesurfer subject. And I'm going to pass it the path to a FreeSurfer subject directory here. So in this case, I want to pass it shared/msd/nsd data other /FreeSurfer originals /sub01 underscore. Gotta make sure I've got this right. Sub01 underscore original. So this gives me back an object that's a subject object. It clearly knows where the FreeSurfer subject comes from. And if I want to make a 3D plot of the surface now, unfortunately, I'm using this interface as Jupyter Lab right now. There's problems with Jupyter Lab and rendering 3D images. So I'm going to copy this address and then paste it in a new window. And I'm just going to delete everything back into this /lab in the title. Can you all see this? Okay, so if you delete all that and then you put tree here, this gives you an older interface for Jupyter that people used to use. But since Jupyter Labs has come out, people prefer Jupyter Labs. It's pretty much the same thing. You're going to recognize it pretty clearly. If you open up this this notebook, it's the same one I've got open over in the Jupyter Labs interface, except I haven't saved it over here yet, so it's empty. So let me just grab some of this. Okay. So this is just a Jupyter interface that looks a little different, basically. But for whatever reason, in this interface, 3D graphics work just fine, and in the other Jupyter interface, they don't, and that's why I went over here. So I'm just going to make a 3D plot here using the Cortex plot function. I'm going to pass it the subs left hemisphere, and I'm going to ask it to plot the white matter surface. And hopefully this actually works. I didn't really test this beforehand, so if it doesn't work, I'll be pulling up a different Jupyter notebook. Oh no, it's working. Okay, so here's a 3D model of the Cortex that you can interact with in your browser. And if I just pick any point on the cortical surface here and I just zoom into it real close, you can see that it's made up of little triangles at the kind of detail level. So this is just like in 3D graphics and video games these days. It's every 3D model you see in a video game is made up of tiny triangles and vertices. And that's just how you make these kinds of 3D surfaces, generally speaking. There's a lot of mathematical reasons for that. Triangles are easy to work with. They're the simplest kind of 2D shape, and that's why we use them. But ultimately, when I say that FreeSurfer tessellates the surface, what I mean is it figures out where the surface is based on the contrast of the voxels, and then it fills that surface with vertices and triangles that are all about the same size. And it does a very good job of trying to make them all the same size, although they aren't, obviously they're not exactly the same size. You can probably see right here that there's 3 little tiny triangles inside of this one, whereas this triangle over here is quite a bit bigger. They're okay. So obviously the triangles aren't perfectly uniform here, but they do capture the surface very nicely. So that's sort of the second thing that FreeSurfer does, is come up with these surface models, which are all made of triangles and vertices. Yeah, so the question is, what are we looking at exactly? This is the boundary between the white matter and the gray matter. So in the T1 weighted image, it's very easy to pick out the white matter and it's very easy to pick out the gray matter. And FreeSurfer will figure out where that boundary is based on the kind of contrast of the voxels around it. They've got a very sophisticated algorithm for doing that. It's called the Watershed Algorithm, and it's a way of kind of clustering over space. There's a lot of papers and stuff on it if you're interested, and the original paper is like 1998 or something like that, for FreeSurfer, that is. Yeah, so let me show you. So the question is, like, should we call this Cortex kind of? I'm gonna show you something here, which is if I then plot the peel surface, and I'm going to give it a little bit of transparency so that we can see through it, by saying mesh alpha equals 0.5. So yeah, so the gray matter is, 2 to 8 millimeters thick or so, usually more like 4 to 6, but depending on where you are in the brain. And so the peel surface and the white matter surface are a little different, and you can see that here. So the partially transparent surface on the top is the peel surface, and the opaque surface underneath is the white matter surface. And you can see that there's a few millimeters of space all along the brain, basically. So this isn't, I call this Cortex because it's the closest representation we have. It's the surface in Cortex, but Cortex, of course, is actually a sheet that's a few millimeters thick. So yeah, so when FreeSurfer does all this tessellation, it tessellates not just the white matter surface, but also the peel surface. And so you've got both of these, and you can use those to kind of to examine different like thickness and stuff like that. A kind of important thing about how FreeSurfer does this process is that when it comes up with the white matter surface, it comes up with a set of like 150,000 or so vertices that capture the white matter surface. It then takes the same set of vertices and displaces them into the peel surface. So you'll never have a white matter surface that has like 150,000 vertices and the peel surface that has 170,000 vertices, and they're not actually related to each other. They're just 2 different surfaces. They're always the same. They're always the same set of vertices, just different coordinates for the vertices. Does that make sense to people? So same vertices, same triangles in all the surfaces. Okay. Yeah, so that's sort of the second set of things that FreeSurfer does, is come up with these surface representations. The third thing that the third major set of things that FreeSurfer does is the cortical alignment to the FS average. So that's the animation I showed at the beginning, where it does the diffeomorphic registration of the spheres to the FS average sphere. And so once you've got that, what you have is a set of these exact same vertices that have been inflated to a sphere and then rearranged so that they're in about the same position as, or they're in a position that corresponds to the FS average surface. So what that means is if you want to take data from one subject and move it over to another subject. So for example, how many of you have used a probabilistic atlas like the Wong 2015 atlas or the Glasser atlas, Glasser 2016? Yeah, okay. So these are very common atlases. They're really useful tools. I don't know. Let me just see if I can pull up. a picture of the atlas for people who haven't seen it. But yeah, this. So let's open for a bigger picture. Okay, so this is a picture of the Wong 2015 visual area atlas. So what they did was they took 54 subjects, I think. They hand labeled all of these areas in all 54 subjects based on experimental data. And then they just aligned them all to the FS average. And they just averaged the boundaries for each of these areas and said, anywhere that most of the subjects have this particular area, we call that the atlas region of the area. So this is essentially a map of the average boundaries across all those 54 subjects. And they do that average on the FS average surface. And then I come along and I have a subject, I've run a T1, but I haven't collected any data for them. I don't have any way to decide where these boundaries are aside from anatomical information. So I just take my subject, I run it through FreeSurfer, their brain gets lined up with the FS average, and then I can just interpolate those visual areas over to my subject. And I have a really good guess as to where those visual areas are. Does that make sense?
Speaking of FS average, my understanding from your first slide was that it comes in activity, so we get our T1s, well, like inside out, so you can get them to the average. So yeah, what you're saying now, I understand is like it's coming from data or
yeah. So for Zoom people, the question was this slide here that I showed earlier makes it look like basically you collect all these subjects and then you make your own average for your own subject pool. And the way I just described it was that there's this one FS average out there. Which is it essentially? And the answer is that it's either. You can, FreeSurfer has the tools to take these T1s and average them and make study specific FS average. Most people don't do that these days because they've taken the Human Connectome Project 1,200 subjects and made a really great average for all 1,200. And the chances that you're going to need a very specific average to your study really just depends on whether you're studying a population that has something anatomically interesting going on. So if you're studying, neurotypical individuals, there's really no reason not to use the Human Connectome Project 1,200 subject FS average. If you're studying subjects with lesions in a particular location, you probably want to make your own, although FreeSurfer doesn't deal with lesions very well, and I can talk about that later if people are interested. If you're studying kids, for example, kids' brains are not like adult brains exactly, so you would probably want to make your own average of kid brains before, rather than use the HCP average, because the HCP average won't fit the kid brains very well. Yeah, but that's a great question. So I actually have another animation that I might real quick show you. If I can remember where it is. Yeah, so no, this isn't actually relevant. Okay. Anyway, other questions about that basic idea of how you can transfer from the FS average over to an individual subject? I can show you an example of that in the code if you're interested. Yeah. Sorry? What other areas have like atlases, like the visual cortex? That's a great question. So there is an atlas that came out of the Human Connectome Project called the Glasser 2016 atlas, which does the whole brain. Now, they have a particular method for coming up with the particular parcellations that they used. And I can't really comment on whether their method produces the correct parcellations of the brain or anything. I haven't studied it that closely, and honestly, I don't know much about the brain aside from visual cortex. So I'm not a great judge of whether they parcellated the frontal cortex very well. But I can say that in the visual cortex, they did a good job of parcellating at least the major areas. They have some beliefs about some of the visual areas that I don't really share in terms of where they are in their boundaries, but that's kind of getting into the weeds. So what I'm saying here is that this atlas does parcellate the whole brain, but it comes with some opinions of the authors. And so you just have to like accept whether or not you think they know what they're doing when they parcellated the brain. There's other atlases. I mostly know about ones for the visual cortex because that's where I work. And also, I think that just the visual cortex is a little bit ahead of a lot of the brain in terms of having like very nicely parcellated areas, because we've got these great experiments we can do that give us really nice maps. And so it's easy for us to parcellate areas relative to like frontal cortex. Also, I do want to say that all of this only really applies to cortex. It doesn't apply to like if you're studying the hippocampus, or if you're studying like the cerebellum. You can in theory run these methods on the cerebellum, but FreeSurfer is really optimized to work with cortex. And I think if you tried to get FreeSurfer to segment the cerebellum, it would probably give you something really weird back. I've never done it, but regardless, this is really about cortex. Yeah. Other questions about any of that? Okay, so in that case, let's just spend a little time looking at, first we'll look at a FreeSurfer directory, and then I'll just kind of do some, or probably at the same time, I'll do a little bit of showing you around this NeuroPython library. So I'm going to go back to this terminal here, and I'm going to cd into this subj01 underscore original directory. And actually, it might make more sense to just do this in the browser. So I'm going to go to NSD data other, FreeSurfer originals, and then sub01 underscore original. Okay, so if you've used FreeSurfer much at all, you probably recognize these directories. These are what you find inside of a subject's FreeSurfer directory. So when FreeSurfer's finished doing all its stuff, you've got these directories. A few of these I'm not going to talk about because I have never had any reason to look inside of them. So touch, I have no idea what this directory is for, and I don't think it contains anything useful. Stats, I have also never had to look inside of. Same with scripts. The important directories, as far as I'm concerned, are label, MRI, and surf. They're the ones that contain all the important anatomical information. So let's start with MRI because that's the kind of the most straightforward and earliest one. This directory is full of what are called MGZ files. So MGZ files are a zipped form of an MGH file, and MGH stands for Massachusetts General Hospital, which is where FreeSurfer was developed. So that's why it's called MGH. These are all volume files. These are basically nifty.nai.gz files. They're just a slightly different format that FreeSurfer has been using for like 20 years. So I believe these predate the nifty file. I'm not 100% sure of that, but I think they've been around longer. But they're just very simple volume files. And so if we come back over to a notebook here, first of all, you can read these using nibabble. So if we import nibabble as nib, you can just nibabble.load, just copy and paste this directory so I don't have to type it all out. But if we take this subject's FreeSurfer directory and we look in MRI and we load brain.mgz, this is going to give us back a FreeSurfer MGH image, which is pretty much like a nifty one image in terms of how nibabble treats it. So these kind of objects, I'm not going to go into too much detail about the image objects, but that's basically what those files are. And then there's just all these different files in here, and a lot of them have very cryptic names. So like what's nu.mgz? I believe that is a normalized form of the brain. So like after they've normalized some of the contrast. But the only real way to figure that out is to go over to this recon dev table I talked about earlier and find nu.mgz in here. And here we have the command. So you can see over here in the table, we see that the output of this step is nu.mgz. And this comes from the first set of operations where the command line to run it is this particular command. And if you go and look up what this command does, you might be able to figure out what nu.mgz is. All of this is, I find, to be very opaque. And in fact, one of the problems I think FreeSurfer has is that this stuff is very opaque. What I'm going to advise is that there are just a few of these that you really need to care about. So the first of them is brain.mgz. Brain.mgz just contains the brain. And it's after it's been normalized and everything and skull stripped, and it's just the MRI of just the brain. So that's a good one to know. Another one is raw average.mgz is basically the T1 after, so what the raw average is it's the T1 in the space of the T1 that as you collected it. FreeSurfer will then, for pretty much everything after almost every step in the pipeline, they use what's called a conformed brain, where they have changed the axes to match their kind of assumptions. So if you need to think about your files in terms of the original orientation of the T1, this raw average.mgz file is that file.
Does that include multiple surfaces? Like, let's say you're thinking about pure surface, like minor surface.
Ah.
Is that a like equal of different surfaces that you would on all one surface?
So let me just show you. So yeah, so the question for people on Zoom is essentially what's in the brain.mgz file. Is it like surfaces, or is it what does it contain? Well, let's just actually look at it. So I'm just going to grab image. So here I've read in brain.mgz for this subject, and just like with nifty one file, I'm just going to say the data array is image.get fdata. Now this is just a great big NumPy array, because this file actually just contains a volumetric image. So let me just import matplotlib, and then plot.imshow, and I'll just pick out this particular slice, and you can see that this is just an image, a volume image, except that the skull's all been stripped and they've normalized all the contrast to be pretty uniform across. Does that answer your question? So these MGZ files in the MRI directory, they contain all the volumetric processing, but none of the surface processing yet. So this is sort of the first many steps of FreeSurfer spit out volumes that have been somewhat post-processed into this directory. There's just a couple others that I would suggest being aware of. One is probably the most important one is the ribbon.mgz. So, and let's just look at what that contains. So I'm just going to change this to load in the ribbon. I'll get the array again, and then we'll just plot it. And now this is a little hard to see what's here, but what we're actually seeing is an image where every white matter voxel has a particular numerical label. Every gray matter voxel has a particular numerical label, and there are different labels for the right and left hemispheres. So the left hemisphere, and I don't know how they pick these numbers, but the left hemisphere has values of like 3 and 41 or something like that. And I'm not sure those are the right numbers, but it's something like that. And then the right hemisphere has values like, I think it's like 4 and 32 or something like that. Anyway, they have some arbitrary values, but they tell you where in your image the white and gray matter voxels are. And an easier thing to do, rather than try to figure out which numbers those are, is you can actually read an lh.ribbon.mgz instead. And that will just tell you where the left hemisphere gray matter voxels are. And similarly, if we read in the right hemisphere ribbon, we get just the right hemisphere gray matter voxels. So typically, if you've done some pre-processing that does something like pull all of the functional voxels that are in the gray matter out of your functional scan, what it's done is it's gone and it's figured out based on the ribbon.mgz in the FreeSurfer file which voxels are in the gray matter, and then it's pulled those voxels out. That's often how those operators work. That'll make sense so far? Okay, let's go on to surface stuff then, because I think volumes are boring. Next is we're going to skip script, stats, and touch, and we'll go on to surface. Oh yeah, no problem.
So on MGZ file, you're still using Voxel term, and because it's volumetric, so we don't have vertices not yet with MGZ file. Is that
correct? Yeah. So the MGZ files typically do not contain vertices. They just contain, really all MGZ files contain are n-dimensional arrays. They're really just n-dimensional array files with a little bit of header data. Yeah. Now that's kind of important because sometimes we do store surface data in the MGZ files. Yeah, and do I have a question from online? Or from? Nope. No one on Zoom asking a question. Okay. Yeah, sometimes we do store surface data in MGZ files, and I'll talk about that in a little bit later here. Okay. So let's look at the surface directory here. This directory, I think, honestly, is even more opaque because there aren't even typical file name endings here. So you'll notice that there are files like l.graymid and l.inflate.nofix and Jacobian white, and these aren't even these don't even have file extensions. And I honestly don't know what drove them to name all the files like this, but this file here, lh.peel, contains the vertices and triangles in the peel surface of the left hemisphere. And you notice that earlier in this notebook, I read that in by asking FreeSurfer to read in a whole subject directory and then plot the peel surface. So NeuroPython will organize all that information for you, so you don't have to remember all these files. But you can also read these files in using nebabble. So just as an example, copy this line. So we'll say peel equals nebabble.load, and I'm gonna go here. So this is the FreeSurfer subject directory, and I can go surf lh.peel. Let's see if that works. No, okay. So that doesn't work because the nebabble.load function only loads certain kinds of files, but nebabble has a FreeSurfer module with an IO module with a read surf function, I believe. No, maybe read surface, or maybe it's read geometry actually. Yeah, read geometry function. And this will read in a surface. However, what it really reads in is two tuples, or sorry, a tuple of two values. The first of which is a coordinate matrix, and the second of which is a triangle matrix. So just to kind of explain what that is, this is how FreeSurfer store, and this is also how the HCP and everyone else stores surface files, is you get the vertices for each coordinate as like XYZ columns, and you get a list or an array where for every row, the three integer indices are the vertices that are part of that triangle. So each of the rows of this second matrix represents a triangle, and the first matrix the first triangle in this matrix has vertex 0, vertex 1, and vertex 5 as its three corners. That's what all that means. And so if I'm going to import a 3D plotting library here, and just if we do a plot of just the x, y, and z coordinates so I'm here, this line, I'm just pulling out the x, the y, and the z as three separate arrays, and then I'm just going to plot them as dots. Oh. You can see that this is clearly this looks like the peel surface. It's just that I plotted it as a bunch of spheres that are all honestly a little big. And so it looks really funny, but this is clearly in the shape of the peel surface, but all this is a bunch of points. Did that make sense to everyone, what I just did there? Yeah, okay. So the LH.peel contains that kind of information. LH.white contains the white matter surface. There's also an LH.inflated. You've all seen inflated surfaces, I assume. It's the inflated. It's not the spherically inflated. It's a partially inflated, so it still has the shape of the brain. Basically, I can actually I might as well just show one. So if we ask for the inflated surface, we'll get this kind of a mesh. And then there's also LH.sphere. And that, of course, is this spherical surface that's been inflated. And then finally, there's LH.sphere.reg. And LH.sphere.reg is also a sphere, but it's a sphere that's been aligned to the FS average surface. So that's where all the information about anatomical normalization is stored. Now, here's the thing I think is really bizarre, is that LH.thickness is not the same kind of file as LH.sphere. LH.sphere contains a surface, LH.thickness, LH.volume, LH.curvature. These all contain surface properties. So when FreeSurfer makes these surface models, it also goes along and calculates the gray matter thickness at every vertex, and it calculates the curvature at every vertex, and the focal depth, and all that kind of stuff. And it saves these out as properties. You can read these properties in using the Babel again. It's a lot like this line here. Let me copy it. So if I want to read in the LH.thickness, for example, for the gray, to get the gray matter thickness at every vertex, I think the name for this function is read morph data. Yeah, morphological data. In MATLAB and a lot of other languages, that's called read curve, because the most common file that people use is lh.curve for the curvature. But regardless, what I don't know why I called that peel. I should call that thickness. This just gives us back an array of values, one per vertex. So this tells us for each of the vertices in these models up here that we've in the cortical surface models we plotted, this is the thickness at each vertex in order. Now, when I was first learning about these surfaces, I found this very unintuitive, that there was like just a list of numbers and that was the thickness for all of these vertices. But the kind of key thing here is that FreeSurfer comes up with an ordering of vertices for each hemisphere, and it uses that in every file. So you always, vertex 0 is always in the same vertex in the peel in the white surface. It's the same vertex in the thickness file and the curvature file. And so you just kind of have this ordering of vertices. And the other unintuitive thing is that you might expect that vertex 0 would be, maybe in the back of the brain, and vertex 1 would be right next to it, and vertex 2 would be right next to it, but it's nothing like that. Vertex 0 might be anywhere on the brain, and vertex 1 could be anywhere on the brain, and there's no guarantee at all that they're going to be next to each other. These vertices you should just consider them to be in a random order, and the triangles link them all together in the correct way. But you can't deduce something about where a vertex is based on what its index is in the array. Does that make sense to people?
Yeah, so we want to get some business of there is 1 point. Direction of the point, it cannot be represented just one number.
So the thickness can be represented with one number because you've got a vertex has a position in the white surface and it's got a position in the peel surface, and you just have to measure the distance between them, and that's the thickness of the gray matter at that vertex. Yeah. So let me show you how to deal with these properties with NeuroPython. So you read in this subject earlier. Oh yeah, go ahead.
Find the closest Voxel, for instance, to any specific.
Yeah, that's actually a little tricky. So you have yeah, so for people on Zoom, the question was, is there a way to find the closest voxel to any given vertex? Basically, especially if you're talking about a functional voxel, your functional image is going to have a different orientation than the FreeSurfer images, and it's going to have a different orientation than the FreeSurfer surfaces. So FreeSurfer does a little bit of rotation to make sure that like the surfaces are roughly aligned with kind of like the MNI brain. So you have to apply a transformation to the surface vertices, and then you can just once you've transformed them into the image space, you'll have some coordinate for the vertex, and you can just round that to integers, and you get the voxel it's in. So if this is something you need for a hack project, I'd be happy to go over that, but I wasn't planning to talk about that because that's many steps and I haven't thought through that in a while. But absolutely, if you want to talk about that after we're done here, I'd be happy to show you. Yeah. Okay, so we have a subject here, and in fact, the subject has some properties or some numbers LH and RH for the left hemisphere and the right hemisphere, and these are what are called cortex objects. And these actually have a dictionary in them called properties. And I'll just get a list of the property keys. And what you can see there's a whole bunch of keys. Here's convexity, which is basically the depth of the sulcus. Excuse me, here's thickness, here's curvature. There's a whole bunch. We don't really have time to go over all of them, but a lot of them are pretty self-explanatory. Some of them are Broadman areas. Some of them are labels for things like MT, motion sensitive area. But regardless, if we look at, for example, the thickness property, this should be equal to the thickness property that we read in with the NeuroHackademy function, because that's what it's using under the hood to read it in. So basically, NeuroPython will organize these areas for you. And in particular, you can plot these things quite easily. So if we wanted to plot the subject's left hemisphere, I'll do this as an inflated brain. You can just tell it to color it according to the thickness. And I'm going to give it the hot seat color map. And this gives you the thickness of your subject like this. Now, I told it to plot the thickness as the name of the property here, but since we read in the thickness as an actual vector, we could also have just given it that vector like this, and that works too. So it's kind of flexible in how you tell it what to plot. Any questions about any of that? Okay, so I know some people wanted to go to the the second half of the bids room because they were talking about receptive fields. So I think that's going to start around now. If anyone wants to run off to that, I won't be offended. Okay, so let's see. I've shown you how to plot things. What else? What else are people curious about with respect to FreeSurfer? I think I promised I would show you how to interpolate between subjects. So let's maybe do that. So let's suppose I've read in the or I've loaded in the Wong 2015 atlas, for example. Well, actually, I think I think I can actually read that in 1 second. Yeah. Okay. So NeuroPython includes the Wong atlas in its package. I just have to remember where it is. So yeah, okay. Yeah, okay. So okay, so I'm just going to say this is the file name for the Wong 2015 atlas. Now, notice that this ends in MGZ, which we know usually contains volume files. This is a unique case where this file does not contain a volume file. It contains properties just like the lh.curve or lh.thickness file. And the reason we store these in MGZ files sometimes is because it's hard to read in FreeSurfer's property files. You have to have a special library to do it. Typically, MGZ files are a little bit more common, and they used to be that you could read them in with NeuroHackademy, but you couldn't read in the curvature files. So for a while, we would just store everything in MGZ files. And MGZ files will let you store a 1 by 1 by 150,000 volume. That's no problem. So you can store something like thickness in the MGZ file, and that's fine. So I'm going to go ahead and say Wong 15 is equal to neuropython.load, this file name. And NeuroPython is smart enough to know that since this is a 1 by 1 by great big number of volume, it's probably just a property, so it'll give us back just a property. And you see it's just a bunch of numbers, most of which are 0, because 0 means this voxel or this vertex is not in a visual area. So let's start by plotting this. So I'm going to start by saying, let me get the and in fact, I want to make sure I load in the FS average the FS average subject from this directory here. Oh, where there's not one in there. Okay, where did you load the FS average from? If I run this, it will work, but it will download an FS average from an online data set, and it will take like a very long time. So I don't want to do that. But there is an FS average somewhere on the server. I just don't know where it is. Oh, is it in your directory? Okay. Well, let's start this running and see how long it takes. So this is gonna load in an FS average subject, but it's going to do it by downloading this great big data set and unzipping it and then loading it in. So it'll take a second. So while that's loading, I'll just try to explain a little more here. So these numbers correspond to, well, I don't have that picture up anymore, but basically for an atlas, you typically just label each of the areas as a number, and then 0 is not in any of these. 0 is like anything else. So like the medial wall would be 0 typically. And in most of the visual atlases that I work with, most of the brain is labeled 0 because it's not in visual cortex. But here we have 21, which is one of the labels. I don't know which one offhand. And so that particular vertex is in one of our visual area labels. So once this loads, what I was going to do is just do make a plot of the FS average surface inflated, and I was just going to color it according to the long 2015 atlas, and compare that to if we try to plot the subjects like this. So anyone have a guess as to what this is going to do when I run that? So it most likely it's gonna give us an error because the number of vertices in this this vector doesn't match the number of vertices on this subject's cortical surface. This vector is for the FS average surface, so it's got one value per vertex on the FS average surface, but two subjects aren't going to have the same number of vertices. It's just that every surface within one subject will have the same number of vertices. So additionally, vertex 1 in one subject is not going to have anything to do with vertex 1 in another subject. FreeSurfer is going to pick where vertex 1 goes kind of randomly, and it's going to tessellate according to its algorithm, but its algorithm includes randomness. So even if you run FreeSurfer twice on the same T1, you will get out different surfaces with different vertices and different orderings and stuff. So that's a kind of confusing and unintuitive thing about FreeSurfer. I believe you can tell it to I believe you can tell it to use a particular random seed, but even then I'm not certain that it always comes up with the same set of vertices. I think there's randomness built into the algorithm, but I could be wrong about that particular point. So my suspicion is that this line will just fail here. If it succeeds, it would probably succeed because there were enough values in this to cover every vertex over here, but it would just look like noise because the vertex numbers in this subject's hemisphere are random relative to the FS average hemisphere. And so whereas in FS average, all the vertices that have, label 21 are all going to be next to each other, in this individual subject, those vertices may be all scattered across the brain. And so that color is going to get all scattered across the brain. It won't make sense. However, this line, because this property actually goes with the FS average surface, this will produce like a coherent set of maps in the image. And in another minute or two, we'll be able to see that. Yeah. Oh, you did. Is it in Slack? Thank you. Perfect. Okay. Okay. Oh, FS average. Is this FS average sub slash what? What did you want to add before shared? Like this? Oh, really? Let's let me just check this directory real quick. There is an FS average there. Okay, I think I can make this work. So this doesn't work. So I think it's failing because it's complaining that it's not finding all the files that it should find in a FreeSurfer directory. So I'm just going to tell it not to check for those, and then it won't. Oh, I think I don't need the slash in this case. Yeah, so it's the reason it's giving this error is because it's not finding some files that it needs, I guess. So I think you were using FS average. Someone was using FS average 5 and it was working, and this was working for you, wasn't it? Okay, so I just loaded in an FS average surface, but I think, yeah, so this is a downsampled FS average, but we'll go ahead and use it for now. That's fine. Well, actually, we can't use it because it's downsampled, so it has the wrong number of vertices. So this is what the FS average kind of looks like downsampled, but that's not very useful. I'm not sure why this isn't working because it was definitely working for you earlier. Oh, you know what it might be? Try one thing here. Okay, well, that's not going to work, unfortunately. So, okay. Because I interrupted it earlier, it now cannot find that one. All right, 1 second. Is there? All right, I'll try it because it'll be faster than loading it this way. Are you going to message it to me again? Sorry, everyone. Just trying to figure out where to load this from. So same path, just that. Okay. Like without this? Yeah, I don't see it here. Does it show up on yours? All right. Okay, well, I'll let this run again. We'll see if it works. Okay, well, while we wait for that to load. Okay, so interpolation. If you want to interpolate this long atlas, we'll visualize it here once everything loads. But if you want to interpolate this long atlas, there's a pretty straightforward way to do it in NeuroPython. You can just basically say, you want to start with the subject that you're interpolating from. So in this case, we're interpolating from the FS average. And we're going to interpolate from the left hemisphere over to the subject's left hemisphere. So the idea is we've got this atlas, this long atlas, that's defined on the FS average vertices. And the FS average vertices, just like any subject vertices, have positions in space. And so this makes this particular map or set of maps that are all kind of coherent on the FS average surface. If we just like, so as I was kind of saying with this attempt here to plot the long atlas on the subject's hemisphere, that would create noise because the vertices don't match up. So in order to take the maps that we have on the FS average and put them on the individual subject, we need to interpolate from one to the other. And what this really involves is taking the spherically inflated FS average brane and the spherically inflated registered subject brane, so the one that's been registered to the FS average, and for every vertex on the subject's brane, finding the triangle that it's in on the FS average brane. And then you've got two choices. One is you can just take the nearest vertex to it and say that's the value I'm going to assign to the subject's new values. So that's nearest interpolation. That's just saying these two sets of points are in register. For every point whose value I want, I'm going to take the closest point in the atlas hemisphere. The alternate way is to do linear interpolation. Linear interpolation is where you, within the triangle, you smoothly, you treat the triangle as like a smoothly varying field of the property where you've got three values for the three corners of the triangle, and there's sort of a linear variance between them, and you pick out the value of that property at the particular point inside the triangle. That probably was not a very great way to explain that. I kind of wish, let me see. See if I can draw this for you. What's that? Great question. Which interpolation is more common? So it depends. I think nearest is probably the most common, and the reason people like nearest is because you don't do any averaging of the data. You're just taking the value that you found and moving it over to the nearest vertex. And in general, I think if you're in doubt, use nearest for that reason, because you're especially if what you have is like labels where you don't want to interpolate labels, because you could have a triangle where you've got these 3 points. These two have label 0 because they're outside of the ROI. This point has label 50 because it's inside the ROI. And if you interpolate between them, you may end up with 25 because you're right in the middle, even though label 25 has nothing to do with label 0 or label 50. So that's an example of where you want to use nearest interpolation. Oh, and this finished. Okay. So let's start by doing this, and the one that should fail. And I didn't read in the one atlas since I restarted. 1 second. Right. So this will either fail. Yeah, it'll fail. So it's just going to basically say you've got the wrong number of vertices. I've got an indexing error, basically. And that's because we tried to plot the FS average long on the subject. But for the FS average itself, for the FS average itself, this should look reasonable. Yeah. So it's a little hard to see the low value labels because this color map isn't very good for this, but black is clearly outside of any ROI, and we have a nice kind of set of maps for visual cortex here based on the long atlas. So let me go ahead and just delete this. So now we're going to take the left hemisphere of the FS average, and we're going to interpolate onto the subject's left hemisphere. And we want to interpolate the long atlas, and we want to use nearest neighbor interpolation. So this will be sub long 15. Now if we do a cortex plot of the subject's left hemisphere, I'll do inflated. And we'll color it according to sub long 15. And now we have the subject's hemisphere with those long labels. And this maybe looks very similar, but if, for example, I do this as the peel surface, it should be pretty clear that we've actually transferred them over to this subject. Did that whole process kind of make sense to people? Okay. Any questions? I think we're kind of, I guess we still got like 15, 20 minutes if people have questions. I'm happy to walk through other stuff if people would like. This was kind of what I planned to show you though. Do you have a question in the back?
Could you talk a little bit about the pipeline for like fitting a first level GLM to surface data?
Oh, okay. So yeah, for people on Zoom, the question is what's the pipeline like for fitting a GLM to surface data? Pretty much the same as it is for volume data. So rather than walk through the pipeline, what I'll say is that here's the difference between if you have a volume and if you have a surface. So typically, let's assume you're processing your data with fMRI prep. When you process your data with fMRI prep, you can say, I want the output to be an M&I space, in which case it'll give you a lot of volume, right? And then you're going to take a voxel, individual voxels, and you're going to do this GLM on each individual voxel, right? Or you can tell fMRI prep that you want the output to be in what's called FS native. And that is FreeSurfer's subject, individual subject native space. And what fMRI prep does is it actually interpolates all of your bold data onto the surface for you, so you don't have to worry about that. And then you just take individual vertices and you solve the GLM for vertices. Additionally, there's FS average space, and that's the same thing, except instead of interpolating onto your subject's vertices, they interpolate onto the FS average vertices after alignment. So if your whole plan is to eventually compare across subjects, and that's what your study is about, it makes sense to use fMRI prep's FS average output. I tend to suggest people use the FS native just because some things it really matters if it's in the native, not most things maybe, but for certain things it really matters. And you can always convert from FS native to FS average with an interpolation if you need to. So that said, it's basically the same though. It's in the end, you just have bold time courses for vertices instead of for voxels. Yeah.
So once you get a model or is that also a feasible approach to getting data?
Yeah, so that's a great question. So essentially, what's the difference, or why should one do it one way or the other? Solving things volumetrically and then interpolating the surface versus interpolating your time series to the surface and solving things on the surface. This is something where it depends. I mean, I don't think there's a consensus answer to this question. On one hand, every time you interpolate, unless you're using nearest neighbor interpolation, you're transforming your signal a little bit. You're doing some averaging to get your linear interpolation. And so there's some risk that you're going to lose some information, or you're going to transform your information in some way. In particular, that can be problematic volumetrically because it's possible that you've got a voxel that's got a very strong signal next to one that has a very poor signal, or that's not really even in the brain, or that's not gray matter. And it's possible that when you interpolate, you're going to get some of that, white matter and some of that gray matter, and you'll get a weird signal as a result. Nowadays, I think fMRI prep is pretty good at not minimizing those problems. But nonetheless, there's always risks when you interpolate. And those risks apply equally to whatever you're solving for, whatever you're turning your time series into. So if what you do is you start with time series in voxels and you turn it into beta weights, and then you interpolate the beta weights, you run that risk on the beta weights. And if you instead interpolate the time series, then you run that risk on the time series. So all that said, in practice, there's very little difference. I do this for visual field maps, which are actually, they vary in a very smooth way across Cortex. So like linear interpolation is the right way to interpolate them. And so we deal with this at every step. And whether you figure everything out in volume space and interpolate to the surface, or you figure everything out in surface space and interpolate to the volume, makes almost no difference in terms of what you finally get. So only in cases where you've got something weird going on, like you're looking at things in a very narrow sulcus where there's a lot of partial voluming effect or something like that, will there be much of a difference, I think. Yeah, but that's a great question. Any other questions? All right. Well, I'm happy to stick around for a while if people want to ask questions or want to see me do something with NeuroPython or whatever. Just a heads up that there is actually if you go to github.com/NoahBenson/NeuroPython, that's the GitHub for NeuroPython. And if you go to NeuroPython-tutorials, there are a small number of tutorials in here that are all wrapped up in a Docker that you can run, and it'll kind of walk you through some of the other stuff NeuroPython does. Just a heads up. But yeah, otherwise, I'd say I think we're probably done, and I'm happy to stick around for a little while. Yeah, thanks everyone.